Jnanam paramam dheyam. Knowledge is supreme.
We will continue our investigation about homological characterizations of regular local rings. So, the main theorem we want to prove is the following. So, theorem, we were preparing to prove this theorem. So, let AM be an Archian local ring. Then global dimension of A is finite if and only if A is regular. This is what we want to prove today. And remember that the global dimension we have analyzed. So, we have proved earlier global dimension of a local ring. Anyway, global dimension by definition it was, this was the definition, supremum of homological dimensions of modules over A. Supremum is over modules in the category A mod. And also I remarked in between that it is enough to consider finitely generated A modules in this. And for local ring, it is the advantage that this is same as homological dimension of the residue field. A, not R. So, we just have to compute homological dimension of this module. Okay, so this will use today. Remember last time we proved a lemma which I will use it today again. So, I will just recall the lemma we proved last time. So, this lemma was, so always today is AM Noetherian local. If you take an element A outside M square, if A is an element in M which is not in M square, then what we proved is, then the short exact sequence of A by A modules of A by A modules that is M by MA, which is clearly an A by A module, then M by AA, which is also clearly A by A module, and the kernel here is by MA. This is clearly short exact sequence, but the lemma says it splits, is a split exact sequence. That means there is a by A module homomorphism such that if I go like this, its identity on this, that is the split, meaning of split, or equivalently the middle one is the direct sum of the outer two. So, immediate corollary to this, same AM Noetherian local, and now assume that let A be in M by M square which is not a zero divisor, and A is not a zero divisor, in A, then okay, if with this situation, if global dimension of A is finite, then the global dimension of the residue ring A by A is also finite. So, proof, this will follow from this. So, what do you want to show? You want to show the global dimension of this local ring is finite. That means we want to show that the residue field has a finite homological dimension over this ring. And what we have given is the residue field of A is a finite homological dimension over A. So given homological dimension of the residue field of this as A module is finite, then we want to show that homological dimension of, see, the residue field is same. So, let us call this ring as A bar by M bar, as A bar module is finite. This is what we want to show. Then to show that yes. Okay, so how do we show that? In any case, we have an exact sequence like this: 0 to M by AA to A by AA, and to this residue field K. K is the residue field of A by M, which is also same thing as residue field of A bar by M bar. This is A bar, this is M bar. So, to prove the corollary, it is sufficient to prove that I want to show this homological dimension is finite as A by A module. So, in the earlier lemma, remember we have the M by AA here. This is M bar, and the split exact sequence was M by MA, A by MA. This was a split exact sequence from the earlier lemma, and we want to show this guy as a homological dimension finite over A by A. Because if you show this as a finite homological dimension, then this is homological dimension 0 over A by A. So, therefore, this will have finite homological dimension. Is it clear? So, enough to show that homological dimension of A bar over of M bar over A bar is finite. If this is finite, then this will be homological dimension finite from this exact sequence. Okay, and to show this is finite homological dimension and this exact sequence splits. So, therefore, okay. So, remember that we have, because the global dimension of A is finite, that is homological dimension of A by M is finite. So, that is equivalent to saying, so that is, so homological dimension of M is finite, and one lecture before we have proved that if homological dimension of a module is finite and if you have a non-zero divisor for a ring as well as the module, then the homological dimension of M by MA is also finite. So, that implies homological dimension of M by A is finite over A by A. This is the lemma we proved some time back, maybe 1 or 2 lectures when we started homological dimension. I should say here not M by A but M by MA. See what was the result we are using it here. If I have a homological dimension of a module is finite and A is a non-zero divisor for A as well as M, then homological dimension of M by M times A as A by A module also finite. I should strictly speaking I should write on the other side. Now this means this is ideal A times M. So this is what we have proved earlier. So because now we know global dimension of A is finite, that means residue field has finite homological dimension over A. That means homological dimension of the ideal M over A is finite. But now the element A we have in the assertion is in A, which is in A is in M minus M square, and if I prove that it is a non-zero divisor for now the module is M and module is the ideal M, and if I have to check this implication, that means that if I have to use this assertion, I will have to justify that A is a non-zero divisor in a ring. That is enough, because if it is a non-zero divisor in a ring, it is non-zero divisor for a module M also. So we will check that in a minute, but then we would get that homological dimension of M by MA is also finite. So look at this exact sequence now. This one we want to prove homological dimension is finite. This one has a homological dimension finite, and this one is a split exact sequence. And therefore, then this will we would finish what we want to get, because direct sum and of a finite homological dimension module is also finite homological dimension. So we only have to check that A is a non-zero divisor. So we need to check that if I have an element A which is in M minus M square, then A is a non-zero divisor in A. No, corollary was yes, but yes. So sorry, this was already I have assumed it is a non-zero divisor. So we don't need to check. This is given. No, you need I will check it when I need it under some assumptions I will have to. I will it is true, but with some assumptions. That's why I have assumed it here. So I will come back to this point. Good, you reminded me. Okay. So that proves, what did we prove therefore in the corollary? Let us recall. If I have an Euclidean local ring, A is an M minus M square, which is a non-zero divisor, then if the homological dimension of A is finite, then homological dimension mod that A is also finite. This is what we have proved. Okay. Okay. So again, this also this anyway it may be repetition, but doesn't matter. Lemma. If I have a non-zero module M, and as usual our A is local and A is in M, which is a non-zero divisor for M, then homological dimension of m by am equal to homological dimension of am plus 1 in general. Both sides may be infinite. So, this, if you like, this also follows from this, right. But let me prove it for completeness, it is not so difficult. So, that will also give us practice for computing homological dimension. So, look at the exact sequence 0 m to m to m by am to 0, and this map is a multiplication by m, multiplication by a, and the fact that it is a non-zero divisor means this map is injective. This is the kernel. So, now to compute the homological dimension, we have to apply Tor. We have to apply tensor product with the residue field and compute the Tors. So, when you write a long exact sequence, what do we get? We get Tor n plus 1 m residue field. Let us call residue field to be k. And then this is the Tor n plus 1. I started here, m by am k. Then the connecting homomorphism will come here, Tor n m k. See, I started here n plus 1, then n plus 1, and then going to n to this, then Tor n m k and Tor n m by am k, and this map is a multiplication by a again, and this is the connective homomorphism. Okay, what do we know now? This is true for, okay, so what I want to check now is this is 0 here. I can put 0 here, because what happens with and what is this map? This map is a multiplication by a. So, when I take this map, I want to put, so this map is a multiplication map by a, but on the other hand it is the factor is k is a by m. So, actually it will be 0 map, because when you take the definition of the connecting homomorphism, it will come from a tensor product, that, and the other factor is a by m. So, and a is in m, therefore, that will become 0 there. So, that means I can put 0 here and forget this part. That means such a sequence is exact, but that will mean that what do you want to prove? That you want to prove that homological dimension is one more. So, this one. So, already if this for large m it is 0, then if this is 0, then this will also be 0. So, that is how this one more homological dimension. Alright, now that address about a by m square. So, that lemma is the following lemma. So, a Noetherian local, and suppose every element a in m minus m square is a 0 divisor. Then every a module of finite homological dimension is 0, is free. Proof. See, there in the lemma we said if A is in m minus m square, if it is a non-zero divisor, then something happens. So, this lemma says if all elements are zero divisors, then the module will have actually finite, not if it is a finite homological dimension, then it has to be 0 actually. Homological free means homological dimension 0. So, and we can always choose, if not if all elements are zero divisor, then things are easier. Otherwise, we can choose a non-zero divisor and apply those lemmas. Okay, so why is that? So, what we want to prove? We want to prove that if M is an A module with finite homological dimension, then we want to prove M is free. That means, and we are over a local ring. So, free is equivalent to saying projective, but that is equivalent to saying homological dimension of M is 0 actually. This is what we want to prove. We want to prove it is free, or you want to prove it is projective. That is equivalent for a local ring. And what is given? We have given that all elements of m minus m square are zero divisors. So, that means we have given that m minus m square, this is contained in the union of associated primes. Everybody, zero divisors are precisely the unions of the associated primes. See, this set is precisely the zero divisors in A. But this will mean that M is contained in this union M square. And of course, we are assuming M is not M square. A is a local ring with the property that M is not equal to M square. Because if M were M square, then by Nakama lemma actually M will be 0 and it will be field case and so on. So, now here by prime avoidance, because M is not M square, by prime avoidance this will imply that M is actually an associated prime. By prime avoidance, because M is not contained in M square. So, that means what? That means this, so that is this M, the residue field A by M will be contained inside A as A module. Somebody is associated prime ideal means this is an annihilator of somebody. This is an annihilator of some element A, but then A by A, this is contained inside A, but A by A is A by M. Oh, yes, A by A is A by M, because you see, you take the map from A to A by M, any x going to x A, and the kernel of this map is precisely M, and therefore this map will factor through this, and it is surjective already. So, therefore, this will be equal. So, therefore, associated prime ideal means a copy of the A by P is contained in A, but I am applying it for M. So, residue field goes inside M, again goes inside A. Okay. So, now let take any module M, let M be any module, with homological dimension HDM equal to n, which is finite. I want to prove M is projective. What happens if n is minus 1? If n is minus 1, that means actually M is actually 0. So, we can assume n is bigger or equal to 0. And look at the exact sequence like that. Now, you see copy of the residue field is inside A, and then you look at the co-kernel of this. So, that means A by K, this is only A module sequence, and I am going to use this sequence to compute homological the torus. So, that means I am going to apply the functor M tensor dash to this sequence and write the homologies. So, we will start again with tor. I know its homological dimension is n. So, tor n plus 1 M A over K, that I started here, then tor n M K, tor n A M A. This is exact, but this is 0 and this is also, this is 0 and for this is non-zero, because the homological dimension is n means tor n M K is non-zero. So, that is this non-zero and this is 0, therefore, it will imply this is non-zero, because this goes inside injectively here, and this is 0 because you see the earlier one is tor n M A. What is the earlier here? Tor n plus 1 M K M A, right. So, that is 0. So, therefore, what we got is this is non-zero. That means what does this mean? What does the tor n M A non-zero means? Means this will mean, this implies n is actually 0, because what is tor n M A? The tor commutes, so I could have done the other way. See, this is same as tor n A M, isomorphic, but A is projective, A is flat. So, therefore, tors, higher tors are 0. If the first factor in the, when you compute the tor, if the first factor is flat, then the sequences will remain exact after tensoring, therefore, there will be no homology. So, this is 0. On the, that was the reason here also tor n plus 1 M A is 0, but here n cannot be more than 0. Sorry. The ring is the ring A as A module is always flat. It's always flat. So, therefore, n is 0, but n 0 means homological dimension 0 means M is projective. So, homological dimension of AM is 0. So, therefore, M is projective, and therefore, M is free. So, that proves the lemma. So, that is the advantage with working with tor, because tor has a property that its tor Mn is isomorphic to tor Nm. That is not true for X, and both the variables tor is covariant. xt is covariant in one variable and contravariant in another variable. So, that is why working with xt is more difficult, but on the other hand working with xt gives better results.